In this hands-on, we're going to explore the practical applications of generator functions and expressions in Python. Our focus will be again on the same three distinct areas we've been covering in all previous hands-ons, these being streaming log processing, genome pattern recognition, and stock price anomaly detection. In this hands-on, each of these examples we're going to go through will be slightly more detailed than before and will help us understand the efficiency and effectiveness of generators in handling large data sets or streams of data in particular. Our first example involves a generator function named log processor. This function is defined to read log files line by line, which is a common requirement in streaming log processing and a variety of other such data processing tasks. The key aspect here is the use of the yield keyword or yield statement. Unlike a regular function that returns a value and exits, a generator function returns a generator object that yields a new value each time we iterate over it. In the context of log processing, this means we can process each log entry as it's read without needing to load the entire file into memory. This approach is crucial for handling large log files efficiently, especially when they're so large that they cannot fit into RAM, or it's simply inefficient to be putting them directly into RAM or any other memory storage that may be in use given the application and the infrastructure. In our second example, we examine a generator function called genome sequence processor. This function demonstrates how generators can efficiently process, say, large DNA sequences in manageable chunks. The significance of this approach is evident in fields such as bioinformatics, where DNA sequences can be particularly complex. By processing the sequence in chunks, the function allows for pattern recognition algorithms to operate on smaller, more manageable portions of the data. Please note that the sequence here is entirely fictitious and has been put together to illustrate the concept that we're trying to deliver here with sequence processing via generators. The contexts that we are covering are very simply to develop a real world practical intuition for you so that you can apply those same principles in whatever field matters to you. Our third example is the stock price anomaly detector you see on your screen now. In this scenario, we're simulating a stream of stock prices and using the generator to detect significant fluctuations, which we define as anomalies. The ability to process each price point as it comes in and immediately flag anomalies is particularly beneficial in, say, financial analysis, where real time data processing is quite often a very important task. Moving on to a more advanced application, taking things up a notch, an enhanced version of our log processing example here called log generator. Now, this not only reads the log file in chunks, but also applies some regex pattern matching to yield only the lines that match a specific error pattern. The integration of regex and chunk-based processing here demonstrates the utility of generators in efficiently processing and filtering large datasets. Our fifth example, stock price generator here, as in this snippet, combines generators with machine learning for stock price analysis. Please note that the machine learning example used here is entirely fictitious. Please do not try this in a real production environment. Here we process stock price data in chunks, apply this model, in this case the isolation forest, for an anomaly detection use case. And this example highlights how generators can integrate with more complex data processing workflows, such as machine learning pipelines. The ability to process data here in chunks is advantageous when dealing again with large data sets, which are typical in machine learning scenarios. Finally, the last of our slightly more complicated examples. Before we go there, if you're interested in why the output here does not make sense given the implementation, the fictitious ML implementation that's been done here, I encourage you to read the write-up that I've put here to explain why that's happening and why the output that you see above does indeed not make sense. So in our final example, complex genome pattern recognition using generator expressions, we're exploring a more complex implementation than before. This function here called find multiple patterns in genome uses a generator expression to efficiently scan a large genomic sequence for multiple patterns as compared to the singular pattern search before. And this is essentially exemplifying the utility of generator expressions in performing more complex operations like pattern matching over larger datasets or streams. Generator expressions, therefore, offer a concise and memory efficient way to handle such tasks, which is obviously quite invaluable in any data heavy field or application therein. So, in summary, through these examples, we've seen how generator functions and expressions in Python provide an efficient way to handle large data streams and data sets or any other similar data intensive use case. They allow for a lower memory footprint and the ability to process data as it becomes available, which is essential in many real world applications like log processing, bioinformatics, and financial analysis. Let's keep exploring these powerful features in our future lectures and hands on sessions. See you there.